the next talk. I'm again delighted to introduce Kamalika Chaudhuri, who will be giving the talk. Kamalika was she was supposed to be here in person, but unfortunately she got the flu earlier this week. So we're really grateful that she can, despite that, she's still able to give a talk through Zoom. Kamalika is a faculty member at UCSD. She works in the foundations of machine learning, and she has done some amazing work. She's very highly regarded in her field. And just as an example of that, she's general chair this year of ICML and has been program chair in the past. Like ICML is like one of the main international conferences in machine learning. So I will let Kamalika talk more about her research now.
Okay. Thanks, Shivangi, for the very kind introduction. I am really bummed I couldn't come. I wasn't in a condition to travel earlier this week, but yeah, I'm really bummed I missed this event because it would have been my first kind of big event in a very, very long time. Thanks. Okay, so I guess what I'm going to talk about is some of my recent research in this direction of trying to understand adversarial robustness in kind of non-parametric classifiers. So what are adversarial examples? Well, I think most of you must have seen this this picture, right? So basically, what happens is on the left, you have this picture of a panda. And then what you do is you add 0.007 times the image in the middle to it, right? And what you get is this image on the right. And I don't know, I mean, at least to me, and I'm sure to most people, it looks like a panda. But it turns out a lot of the state-of-the-art neural networks are completely convinced that this is a gibbon. And, for those who don't know, because I get this question quite often, a gibbon is a type of monkey. So, a lot of the state of the neural networks are very convinced that this is actually a monkey, right? And so, so what these are basically really small perturbations to legitimate test inputs. And that causes misclassification. So that is these are that's adversarial examples. And when we are talking about panda and gibbon, you might be thinking that this is a bit of a frivolous example that well, there was a panda, you misclassified as a gibbon. What's the big deal? But this can actually get quite serious because if instead of classifying pandas into gibbons, if you classified a stop sign as an yield sign and you had that classifier in your self-driving car, that could be a more serious thing, right? That could be a more serious issue, right? So as a result, what has happened is that a lot of work has gone into, over the last, I would say 5 or 6 years, a lot of work has gone into trying to understand, adversarial examples, how they come from, how to defend against them, and things like that. Okay. So what is known about adversarial examples? So right now, there's a very large number of attacks. So we know how to attack neural networks very, very well with like really minor perturbations, and not just neural networks. We know how to do attacks very, very well. There are also quite a few defenses that work reasonably well with mixed success, I would say, because sometimes they lead to loss in accuracy. But there are quite a few defenses. But at the time when we had started looking at this, and this was maybe a couple of years ago, so most of the work that I will talk about has been published in the last couple of years. So this is so we started working on this a few years ago. There wasn't a lot of understanding on why adversarial examples happen, what's going on, how they fit into the framework of learning, traditional learning theory, and that's kind of what I'll talk about today. Okay, that why do adversarial examples happen? Okay, so let me start with a bit of a background. So the kind of problems we are looking at over here is classification. So what is classification? The idea is, it's very, very simple. It's you have these xi, yi pairs, right? Xi's, think about them as vectors of features, and yi's are discrete labels. So, these labels could be panda versus gibbon, or it could be dog versus cat, or there could be multiple labels as well, right? So there are a bunch of discrete labels, and your goal is to find a prediction rule. Usually this is a prediction rule in a particular class, so it could be a linear classifier or a neural network and so on, that would predict the y's from the x's. Okay, and in traditional learning theory is built on, what is called the statistical learning framework, or kind of the pack learning framework. And here what happens is that there is an underlying data distribution, right? So there's some underlying data distribution D, and both your training and test data are drawn from this underlying distribution, right? And what happens is that what you want to do is to find a classifier that maximizes accuracy according to this distribution. So what is accuracy? So the accuracy is the fraction of examples that is drawn, fraction of labeled examples drawn from this distribution where f of x is equal to y, right? So where you are predicting the right label, where your classifier is predicting the right label, right? So this is your accuracy. And what traditional learning theory has always done is it has been focused on maximizing this kind of accuracy. Okay. So how do we think about robustness in this framework? So when we think about robustness, what we are going to do is we are going to add an additional measure of robustness. And we say that a classifier is robust with a radius s at a particular data point x if for a distance metric d, if your distance between x and x prime is less than equal to s, then f of x is equal to f of x prime, right? So what this means is that we'll be predicting, so if you look at your legitimate test input, you would be predicting the same label in a small ball of radius s around this test input, right? So if you, going back to our panda versus gibbon example, if you imagine your panda to be this image, right? And then a little bit around this image in a small ball of radius, in a small ball around this image, you would be predicting panda instead of predicting, predicting something else, okay? And if it is robust with radius s at this particular point x, what this means is that there's no adversarial examples around x, okay? How do we combine robustness and accuracy? So the way we would do this is through a measure that we call astuteness, right? And we'll say that, if you are astute at a point x with a radius r, means that you're predicting the correct label at that point, and you're predicting the same label in a ball of radius r, right? And so what we care about is, for robust classification, we don't just care about the accuracy, but what we care about is astuteness, which is the fraction of points where your classifier is both robust and it's accurate. And what we will try to do in robust classification is maximize astuteness instead of maximizing just the plain accuracy. Okay, so that is our goal. Okay, so now let us, with this background in place, let us come back on why do we have adversarial examples. Now, if we go back to kind of classical learning theory and we try to understand what might happen, well, one of the possibilities is, we may have adversarial examples because our data distributions, either they're overlap or they're very close to overlapping, right? So maybe pandas actually do look like gibbons. They're just, a tiny bit different, and so you can't have both robustness and accuracy. So this is one possibility. The other possibility is that maybe pandas and gibbons, they look very different, but we don't have enough samples of pandas or enough samples, right, to be able to tell them apart properly. Right, so maybe that's the reason why we had these adversarial examples. And then the third possibility is that we are using the wrong algorithms, right? So once you have the samples of pandas and gibbons, what we are trying to do is we are trying to find some classifier which, which separates the pandas from the gibbons, which sets them apart. Maybe what we are doing is we are using the wrong algorithm to find this classifier. So there are many classifiers are possible, and different algorithms will give you slightly different ones. Maybe what we are doing is we are using the wrong classifier, we are using the wrong algorithm, right? So these are the three possibilities. And I'll give you the answer ahead of time. So the answer is basically 3. Right? So it's basically 3. And now for the rest of the talk, I will try to convince you that 3 is really the answer. Okay. So that's where we are going to go from here. Okay. Okay. Any questions before I get to, any questions before I get into more details? Okay, so let's then go ahead a little bit. And so the context in which we will be looking at these problems is in the context of non-parametric methods. So what are non-parametric methods? These are these really simple kind of classifiers, pattern recognition methods that people have been using for a long time. So these are, things like k-nearest neighbors, where the idea is that you look at your closest neighbors and then you predict a majority label of these neighbors, right? Another example of non-parametric classifiers are decision trees, right? So based on data, you build, kind of a tree of rules like this, right? Like the example on the slide. And so these are 2 simple examples, but there are more complicated examples as well. So there are things like random forests, which are much more, complicated ensembles of trees, or things like kernel classifiers. So there's a whole bunch of there's a whole bunch of classification methods that fall into this category of non-parametric methods. Okay. So what is known about non-parametric methods? Well, before I get to that, I need one last definition, which is that of the Bayes optimal classifier. Okay. So what is the Bayes optimal classifier? This is the classifier which has the highest accuracy on the data distribution. And it's, notice that this is a function of the data distribution. So what this means is that you can't get to it in the finite sample limit, but it is reachable only in the infinite sample limit, right? So as you get more and more samples, you can get closer and closer to the Bayes optimal. Okay, so it's a distribution quantity, and it's kind of a limit, distribution quantity. Okay. So what is known about non-parametric methods? And this is due to a theorem by Stone in 1977. And what Stone showed was that as the training data size grows, the accuracy of many non-parametric methods converges to the accuracy of the Bayes optimal. So, things like nearest neighbor, decision trees, and so on, if you construct them properly, and there are some details that I am ignoring a little bit over here, but if you construct them properly, as your data size grows, they would get closer and closer to the Bayes optimal, right? So in the limit, in the large sample limit, they would be doing, the right thing. Okay. Okay, so this was for accuracy, but what about robustness? So to look at robustness, let me start out with looking at well-separated data. Okay. So what do I what do I mean by well-separated data? So it turns out when we are looking at our robustness, the notion of robustness that becomes is something called r-separation, right? And we say that our data distribution is r-separated if when you have 2 points, x, y, and x prime, y prime, drawn from this distribution, if y is not equal to y prime, then the distance between x and x prime is at least twice r. Right? So what this means is that if you have points with 2 different labels, they are at least distance 2r apart, right? And why is this definition interesting? So the reason why it's interesting is because if this, if your data distribution is r separated, then there is a classifier that is astute at radius r, right? So it means that, if your data distribution is R-separated, there at least exists a classifier which is going to be astute, which will be, which will have astuteness 1 at this kind of radius R. Now, whether we can find it or not is a different matter, but there exists such a thing, okay? So now let's see, for this kind of R-separated distributions, if we can have an analog of Stone's theorem. So to have an analog of Stone's theorem, let us first try to understand what could be the limit of robust classification. So it turns out the first kind of interesting thing over here is that even if your data distribution is R-separated, your Bayes optimal will not be the right limit, right? To understand this, look at this kind of toy example. Here, your pluses, you have these two regions, which are your pluses and minuses. If you look at these blue lines, all these blue lines are Bayes optimal, because the Bayes optimal is undefined outside the support of the distribution, so that so long as you are doing the right thing inside the support, outside the support, you can do anything. But if you look at these blue lines are actually not robust, because, as you can see, these blue lines, they pass very close. You can see one of them passes very close to the gray distribution. So it's not going to be robust. And it turns out you can actually define the right robust analog. And this is something that we call the r-optimal. And this can be defined as the classifier that maximizes the astuteness instead of maximizing the accuracy. Okay, so what does it look like? So it turns out you can write down a formal definition to give you some idea of what it might look like. Here is an example of what it might look like for a distribution that is R-separated, right? So, and again, this is just like the Bayes optimal, the R-optimal is also not unique, but this will be an example. You predict plus if you are within distance R of the support of the positives, and you predict minus otherwise. So you can show that this will have astuteness 1. So it is A R-optimal. But this is not necessarily D r-optimal, right? Like there can be multiple r-optimum even for R-separated distributions. Okay, so this is the right limit. And now the question is, can we actually converge to the r-optimal? And it turns out, something went wrong with my slides. So the question is, can we converge to the r-optimal? Sorry, I should have, So question is, can we converge to the r-optimum? And it turns out that we can do it, but let us start. So to understand when we can converge to the r-optimal, let us look at maybe a couple of, a little bit more of notation. So let us look at how can we represent this very general non-parametric classifiers. So it turns out these non-parametric classifiers that I just talked about, they can be represented as something called weight functions. And this is something which was shown by Stone. This is essentially from Stone's theorem. And what do weight functions look like? Well, weight functions look in the following way. For every x, which is a test point, what you can do is you can get a weight ws comma I of x, right? This is the weight of x due to due to training point I in a training set S. Right? And what you can do is you can write ws of x is the sign of, and here I'm talking about binary classifiers, summing over all your training points, y goes from 1 to n, yi times ws of s comma I of x. Right? And it turns out many of your common non-parametric classifiers can be represented in this form. So for example, if you're talking about nearest neighbors, wsi of x is 1. If xi is one of the closest neighbors of x. So if you're doing, for example, one nearest neighbor, then this will be 1 if xi is the closest neighbor of x in the training set S, and it will be 0 otherwise, right? And then what you will get over here is exactly the one nearest neighbor classifier. For decision trees, WSI of X could be 1 if Xi is in the same cell of the decision tree as this point X, right? So you can represent decision trees also in this particular form, right? So this is kind of a general form in which you can represent a lot of these non-parametric classifiers. And here is the main theorem of our paper. So the main theorem that we can prove is your weight function, your non-parametric classifier represented as a weight function will converge to the R-optimal if the following condition holds, right? And the condition is the following: on expectation, you have this supremum over X prime in a ball of radius A around, and this is for all A less than equal to less than equal to B. Supremum for X prime lies in a ball of radius A around X. Some of these weights, right? So sum over I equal to 1 to n, the weights of, this WSI of X prime times the fact that X prime, times X prime that lies outside a ball of radius B goes to 0. Right? So this is kind of the condition. So what does this condition mean, right? So let's take a quick look at what this condition means. What this means is the contribution to WS of X, right, from points that are not local to X, that contribution goes to 0, right? And so what does this mean? Well, basically what this means is that as you get more and more samples, your classifier becomes more and more local, right? That's at an intuitive level, that's kind of what this contribution is saying. And now if you look at the Stone's theorem condition, the Stone's theorem's condition is also similar, but the difference between Stone's theorem and our theorem is our condition is a little stronger. Our condition says this, not only for x's that are drawn from the data distribution, but also for X prime that lie close to those x's, right? So Stone's theorem means that this kind of locality condition applies only to the data points X that are drawn from the distribution. Our theorem, it applies to not just those points, but also other points in balls of radius A around them. Right? That's kind of the difference. So our condition is a little stronger. But what is interesting is that because of this strength, right, that because of these extra conditions, it turns out that, we have some classifiers that converge to the base optimal, so that satisfy the conditions of Stone's theorem, and so they converge to the base optimal, but not to the R optimal, right? And it turns out these classifiers are, histogram classifiers, which, statisticians have been using for a while, and decision tree classifiers, which, most of us have heard about, right? And so these are the, so our result of our theorem is that these classifiers would converge to the base optimal as n goes to infinity, but it won't converge to the R optimal, right? What happens over there? So to give you some intuition about what is happening over here, let us look at this example of decision trees, right? So here what is happening is you have the, the red points and you have the gray points, right? Those are your two classes, and they are separated. You can see that their distance are apart, right? And if you used a standard decision tree algorithm to construct a decision tree, what that algorithm would do is it would find a one node tree, right? A single node tree, which is represented by this blue line. That is your decision boundary. On one side, you have gray, on one side, you have red. And what it would do is, because it has accuracy 100%, it would just stop, right? It would stop at this point. This is your decision tree. Even if you had an infinite number of samples, it would not do anything more, right? But on the other hand, there is a decision tree which classifies these robustly. It's this super zigzaggy decision tree. And I've tried to draw an approximation to it. There's this zigzag black line. It's a super zigzaggy decision tree. If you could get to that decision tree, then you would classify things by, you would classify things, not only would you classify them accurately, you would also classify them robustly. But the current decision tree algorithms are not going to find it because they're just going to stop when they hit 100% accuracy, right? So this is kind of what happens. And what you can see is, what I had claimed earlier, that here at least what is happening is that the problem is the training algorithm, right? So if you, even if you have an infinite amount of data, even if your data is R-separated, even then, things like decision trees are not going to find the right classifier. And the reason for that is that we are using the wrong algorithm, okay? So that's what is going on with robustness. Any questions at this point? Okay. Okay. So
question, Kamalika.
Yeah.
I wanted to ask, what is the difference between your objective and just maximal margin classifiers? Because basically the classifier you showed, which is optimal, is just the maximal margin one, right? Or very close to it.
Yes, that is in fact a very, very good question. In some sense, we are not really looking for max margin. We are kind of looking for a classifier which has margin at least R. And in fact, in the a little bit down the road, we will make a somewhat more formal connection, and we'll come back to that. That's a very good question. Thank you.
One more question.
Uh-huh.
Hi, so my question was about this notion of robustness. I understand why I imagine it would be good at stopping the panda given thing, because the noise is sort of uniform, sort of makes sense that sort of like based on our like normal mathematical notions of distance. But I guess my question is, does this robustness notion work for like the don't stop sign thing, where like it might be like high Euclidean distance, but like there's some other notion in some sense in which like this is still obviously a stop sign. Does that sort of make sense?
Right. No, it does. It definitely makes sense. So I guess there's a couple of answers to this question, and it's a very good question. Thank you. So one thing is that, to some extent, understanding how to get around these Euclidean notions of robustness can give us insights into how to get around more complicated. I absolutely agree with you, right? To get around more complicated notions of robustness. So a lot of these ideas, and which leads to my second answer, which is people have tried to do robustness in, for example, a feature space, right? So instead of looking at robustness in the Euclidean metric space, what you could do is you can look at the representation space, where kind of traffic signs are kind of clubbed together, and you could also impose robustness in in a more complicated metric space. And a lot of the ideas that a lot of the ideas actually go through. It's just much more expensive because calculating that representation is a lot more expensive. But a lot of the ideas that and a lot of the insights that we learn do go through for those more complicated notions of robustness. I don't know if that answered the question.
That totally answers my question. Thank you.
Thank you. Okay, so excellent. So we talked about robustness, and we talked about how it depends on the training algorithm. We looked at kind of the well-separated case. Now the question is, what about the more general case when your data is not well separated? It might be overlapping and so on. So in this case, one of the first questions here is, how can we define the R-optimal, right? Like, in this case, the question, because we had the R-optimal, we can talk about convergence to it. Now the question is, how do we even define the R-optimal, right? So it turns out that you can do it here in the following way. So what you could do is, you could do it here in the following way. Suppose you have your robustness radius R, and suppose you have a classifier which is predicting a label J in this set S sub J, and it's doing this robustly. Then it turns out that you can write down the following constraint, right? So if you have a classifier which predicts label J in a set of S sub J and is robust in the set, then the distance between S sub I and S sub J has to be at least twice R, right? Otherwise, you could not have been robust there, right? So this is, you can write down these constraints. Then it turns out, if you are predicting robustly in, you're predicting label J and you're being robust in S sub J, then you can also write down the astuteness in terms of these sets S sub J, right? And the astuteness is you sum over all the labels 1 to k, and then you look at the following, right? So you sum over all these labels 1 to k, and then for label J, you have set S sub J, and within set S sub J, you integrate over the, you're basically integrating over accuracy, right? How accurate are you in this set S sub J? Subject to the fact that S sub I and S sub J are distance at least twice R apart, right? And you can look at this, and this suggests the following limit classifier, right? So what you do is you look at these sets S sub J, right? And you maximize this objective, which is the astuteness, over these sets S sub J, right? So, given a robustness radius R, you pick S sub J to maximize the objective, and objective is your astuteness, subject to the constraints that the distance between S sub I and S sub J is at least twice R, right? So if you could solve this optimization problem, it's a really complicated optimization problem because, your variables are, all subsets of your instance space, right? And these could be really, really complicated subset. But if you could solve this optimization problem, then you would have your classifier, and your prediction rule would be you predict label J if you are within distance R of this set S sub J, right? So if you could solve this, then you would get your classifier, and that would be your R optimal. Okay, so this will suggest the classifier. Now the question is, okay, so now we have a limit in theory. The question is, how can we somehow approximate this limit in practice, right? How can we get some sort of actual real classifier that converges to this limit? And it turns out you can, if you, you can at least get one approximation if you think about representing each set S sub J by a subset of training samples. And it turns out that it leads to a very simple combinatorial problem. So your really complicated optimization will become, if your S sub J, instead of being arbitrary subsets of your instance space, if there are a set of samples, it turns out this will become the following. It will become the, it will basically reduce to finding the maximal subset of training samples where points with different labels are distanced 2R or more apart, right? This will be your combinatorial problem. And then, how can you solve this? Well, one way to solve this, so it turns out that for binary, this will reduce to maximum bipartite matching. With a little bit of math, this will reduce to maximum bipartite matching. So you can, you can construct a graph and then find the matching in the graph that will give you this subset of samples. For KRE, if you are looking at, instead of binary classification or K labels, then it will reduce to independent set. Of course, this is, hard to approximate and hard to solve in many different ways, but you can at least use a greedy algorithm for it. And so your algorithm will become the following, and we call this adversarial pruning. Your algorithm will become, you have your training set, you find the maximum subset of training samples where points with different labels are distanced 2R or more apart, right? So you find this subset of your training set, and then you build your favorite classifier on it, right? You can build nearest neighbors, decision trees, random forest, whatever your favorite non-parametric classifier was, you can build this classifier on it. And it turns out the surprising thing is, if you call, so this is, this, we call this adversarial pruning. So if you combine this adversarial pruning plus something like nearest neighbors or kernels, which actually worked on well-separated data, then we can also converge to our optimal in the large sample limit. And this is a little bit surprising because now, after adversarial pruning, your training set has all manner of dependencies. It's not an independent training set anymore. But it turns out that at least in the large sample limit, you can still get this kind of asymptotic convergence. And it turns out it also works reasonably well in practice. So we did some experiments with them, and it does hold up, right? Like, removing this kind of, taking away data doesn't hurt things too much. And you can actually do this, and it also works reasonably well in practice. Okay, any questions so far before I move to my third part, where I will talk about connections to max margin? Yes.
Kind of like two related questions is, how do you decide which subset to prune? Like if there was a S4 that's kind of superimposed on S1, do you like get rid of all the S4 points that are within radius of S1 points, or do you get rid of the S1 points that are within the radius of the S4 points?
So what you would do here is you would build a graph where I think what you would do here is you would build a graph where 2 points, if they are within distance r and have different labels, then you are connecting them by an edge, and then you find the maximum independence set in the graph. So I guess what would happen would depend on the relative sizes of S4, right? Like removing S4, you may end up removing a lot of points, in which case you wouldn't. So that's kind of the main idea.
Okay. Sorry, I just also have a follow-up question. So then with like with inputs like image or text, like would this depend on which representation like you decide to use to get the X's? So like, would you want to like, would this be just much harder for certain representations than for others? And how do you like, I guess, incorporate that?
Yeah, that's a very good question. So here, I should have mentioned this. The distance metric that you would use when you build a graph, right? When points within distance twice are connected, right? The distance metric would be the distance in which you are measuring adversarial robustness, right? Like, if you remember for adversarial robustness, you have a metric, right? That within balls of radius r, you should be predicting the same thing. These two should be the same metric. So, so for some metrics, if it's a very complicated representation and then you are looking at distance in that metric, then yes, calculating that metric itself is really hard. But then once you have the graph, then you can apply the combinatorial algorithm on top of it.
Thank you.
No other questions.
Okay, thanks. Okay, so in conclusion for this part, we looked at this r-optimal, which was a large sample limit for robust classification, and then we showed conditions under which classifiers converge to this limit, and then we found that things like nearest neighbors and kernels converge for well-separated data, but not things like decision trees. And then for non-separated data, we looked at adversarial pruning, which would remove a bunch of the data points, and then we showed that this worked. And kind of the conclusion, at least for non-parametric methods, is that the training algorithm is what is to blame. Okay, now let us think about how we define robustness, right? Like when we get back, let us think about how we define robustness. So, given the fact that we are looking at our robustness, we know what to do, at least in the large sample limit. The question is, does this in fact give us the most robust solution? Okay. And to understand if that is the case, let's look at an example of what happens when your data is heterogeneous. And this does happen a fair bit in practice when, the scales, if you have heterogeneous data, the scales in one region of space, distances in one region of space is quite different from the distances in another region, right? So if you look at this example over here, what is happening is your class, your red class is kind of multimodal, right? There are two small clusters of red and gray, which are somewhat close. And then there is a large cluster of red a long distance away. So think about, I don't know, maybe the reds and grays over here are like cats and dogs. And then the other red is some very kind of unusual kind of cats, like maybe tigers, right? Which look quite different, right? And so what would happen if you are trying to do robust classification in this case? Well, what might happen is because of the way we formulated the problem and we chose this one radius r, we may end up with lacking both accuracy and robustness, right? So for example, if you look at these blue decision boundaries, if you look at the blue decision boundary where we are trying to get to, you have some radius r and you're trying to get to the r optimal, here you are sacrificing, if you are looking at the left where the red clusters and the gray clusters are close, you are sacrificing accuracy for robustness, right? You may be able to get robustness, but you may be sacrificing accuracy because you can't get both at once. Whereas if you are looking at what is happening to the right, your blue line, it's also not giving you the most robustness because it's much closer to the gray part than to the red part on the right? So you are, because of the way you formulated the problem, you are getting neither accuracy and nor robustness, right? Whereas if you looked at this green solution, then this green solution knows that when, it's kind of a data dependent notion of robustness, right? So this green solution knows that, when you are in the left part of space, close to, where the clusters are close, you should go through the middle. So you should get accuracy and sacrifice robustness. Whereas on the other part of the space, you should be more robust, right? In some sense, this is what a max margin style classifier would do. When it can, it should get robustness. When it can, it should get the most robustness it can manage to get. Whereas when it is in a part of space where the clusters are close together, it should try to get accuracy and sacrifice robustness, right? So how can we get to this kind of data-dependent notion of robustness? Right? And how can we formulate robust classification to address this? And it turns out that we can do something in terms of, in the context of these non-parametric classifiers, okay? So how can we formulate such a thing? So before we get to how to formulate it, let us maybe look at a couple of conditions, like what are some of these ideal conditions that a formulation should satisfy, right? So one ideal property that we would like to have is at least that we shouldn't have much of a robustness accuracy trade-off, right? Like, we should try to get accuracy when we can, and then, we should try to get robustness as we can. Right? So there shouldn't be a robustness accuracy trade-off, right? The second condition is that we should try to get some sort of data-dependent robustness in the sense that we should try to get more robustness when the data is better separated and maybe not as much when data is not well separated. And finally, we should try to get something that is at least achievable by, some of the existing algorithms. It doesn't have to be the case, but, ideally we should try to get something that is achievable to either some of the existing algorithms or maybe some modifications to the existing algorithms, right? So these are some of the properties that we would like to have, okay? So recall in the standard learning setting. So let's now start out with trying to see if we can get, like a large sample limit object, which does that, right? In the standard learning setting, what we were trying to do is we were trying to maximize accuracy. And the large sample limit that we had was the Bayes optimal classifier, which maximized accuracy on the distribution, okay? Now, in the r-Robustness setting, what we did was we went from accuracy to, we changed our limit. We were trying to maximize astuteness, and this gave us the r-optimal classifier, right? Where we maximized robustness within radius r, okay, or astuteness within radius r. And it turns out, as we saw that is also not enough. And it turns out that we can, in fact, extend this idea. And we can get to a different notion of a limit object, which we call the neighborhood optimal, okay? So what does the neighborhood optimal do? Within the support of the data distribution, it's going to predict with the base optimal, right? So inside the support of your data distribution, it does exactly what the base optimal does, okay? And outside of the support, what it's going to do is it's going to predict with the base optimal of the closest point in the support, right? So if your point is inside the support, you're done. You just go with the base optimal. If your point is outside the support, you find your nearest neighbor in the support, and then you do what the base optimal does inside that point, right? And this is what we call the neighborhood optimal, okay? So, so essentially what we are looking to do over here is you are looking at, for a point X inside the support of your distribution, your robustness region are the points that are closer to X than to the support of a different label. And what you are trying to do is you are trying to get accuracy, right? Inside your support, you get accuracy, and you want to predict. You want to make the same prediction in the robustness region of X for X that are drawn from this data distribution, right? So you get accuracy, accuracy you try to maximize as much as you can. And then outside the support, you just predict with, you just make the same prediction as the as in the robustness region, right? So that is the main idea. Okay. Now let's see if this at least this limit object satisfies our conditions. It will satisfy no robustness versus accuracy trade-off, because remember, accuracy, you only care about accuracy in the support of the distribution, and you always agree with base optimal in the support, right? So it's not going to sacrifice accuracy. It will give you data-dependent robustness. And in fact, if you look a little bit more closely at this example that I talked about, where there are two close clusters and one cluster that's far apart, it's going to do absolutely the right thing, right? Because, the clusters that are close together, it's going to sacrifice, within the support, it's going to do what the base optimal does. So it's going to, focus on accuracy. Whereas if you were looking at the region, kind of the region on the right, then it is going to go through the, then it's going to kind of predict with the nearest neighbor. And if you look at the decision boundary, basically it's getting, it's going to go, go max margin in that area. Okay. And then, is it achievable by existing non-parametric algorithms? Let's look into that. Okay. And it turns out it is in fact achievable. And in fact, under some conditions, many non-parametric methods would converge to this neighborhood optimal in the large sample limit. And, we can show an analog of the theorem that I had talked about earlier. And it turns out, again, the conditions are stronger than what we had before. So nearest neighbors and kernels would converge with some slightly more stronger conditions. But then, again, things like decision trees or histograms, they are going to converge to the base optimal. They will follow Stone's theorem, but they're not going to converge to this particular formulation, right? They're not going to converge to the neighborhood optimal. And, this is kind of to be expected, okay? So in summary, we can get a data-dependent formulation of robustness. And, if you look at what our formulation does is in comparison with the standard formulation and our robustness, what we are trying to do is we are trying to get accuracy plus a particular form of max margin robustness. Okay. In the large sample limit, for standard, we had base optimal. For our robustness, we had R optimal. Our formulation, the optimal is something we call a neighborhood optimal. And if you look at algorithms, in the standard case, things like k-nearest neighbors, kernels, and decision trees, that would all go to the base optimal. For r-Robustness, you would need to do this kind of adversarial pruning, followed by things like k-nearest neighbors or kernels. Whereas in our case, you don't need to do the pruning at all. Standard k-nearest neighbors and kernels will converge to this neighborhood optimal in the large sample limit. Okay. And so in conclusion, we looked at a new formulation which, of data-dependent robustness, which resolves some of the issues that are present in the standard formulations. We also showed that things like nearest neighbors and kernels will converge to it in the large sample limit. And the open question here is, are there better formulations, right? Are there more optimal formulations? Are there better formulations? And this entire space is really open of how to define and get to data dependent robustness. Okay, so finally, these are our references, and I will finally end with the pictures of my collaborators and students who did a lot of the work. Thank you.
Any questions? Okay, so then so is the panda now, is it still a given, or does it, when you apply it, your work, like in an example like that?
So a lot of the standard neural network defenses like adversarial training, it will stop the panda from being a given. But there are very, very good attacks that you can use to get around it. Because, for neural networks, everything is NP hard. So you can't really give guarantees. But they are, there are better and better attacks coming up. So they are still attackable.
One more question. Yeah.
I'm wondering, do you try to formalize like how hard it is to achieve robustness based on how many points you had to prune?
No, that is a very good question. So what you are saying is you could measure, maybe you could give some estimate of a certain distribution and say that, look, this region, we can't really hope to get both robustness and accuracy, right?
Yeah.
That is a very nice idea. We certainly have not looked at it, but I think that could be really nice and promising. Yeah.
Any other questions? Not then. Thanks, Kamalika.
Thank you.